Hello everyone. After watching several videos on bending in beams, from the flexure formula to shear force and bending moment diagrams to shear stress to built-up beams and statically indeterminate beams and the deflection formulas, now the last topic I want to talk about is composite beams. So composite beams are the ones that are made of more than one material, and you can see them in sandwich beams, you can see them in reinforced concrete, and so on. So the thing is, how do you look at the distribution of strain and stress within such a cross section that has more than one material? The first question you might ask is, why do we have these beams in the first place? Why should we not make the whole thing out of a single material? Where there are several reasons. For instance, if you look at the sandwich beam like this, where you have two flanges on the top and the bottom, or two plates made of metal, and then this core here is made of a softer material like wood, you might say, why don't you make the whole thing out of aluminum? Would that not make it stronger? Of course, but remember that, first of all, aluminum is heavier than wood. Okay, so it makes the whole beam heavier, which adds to the stress. And also, of course, it's more expensive, so it adds to the cost. So, and the other thing, if you remember, sigma is maximum at the top and the bottom. If you remember, if this is the neutral axis, so the normal stress distribution is linearly increasing from 0 to the maximum at the top and the bottom, right? So here it could be compression, it could be tension, or backwards, but basically this maximum load carrying part of the cross section is the top and the bottom portion. So maybe those areas you want to keep them stronger, and in the middle you don't need it to be as strong, first of all. Second, you want to, as I said, keep it lighter weight and cheaper. And since this middle section is not as heavy and cheaper, what you can do is you can increase the height of it. So you can increase this H, make this core a little bit taller. When you make that core taller, remember IZZ, which appears at the bottom of sigma. The bigger it is, the smaller the stress going to be. And remember, if the whole thing is H and B, that was BH cubed over 12. So if I can increase this H even by a smaller percentage, because it's cubed, I'm going to make this I much bigger, and bigger I means a smaller stress, as I said. So not only I fill this area between them that does not carry too much stress, I can also increase the cross-section moment and bring down the stress. Also, it is going to support against buckling, that we'll see later. So the best way to do it is something like that. Or for instance, reinforced concrete, where you have these blocks of concrete here. So this is concrete. And as you know, concrete is really good against compression. But when it comes to tension, if a column of concrete is undergoing some tension, it is not really good and it starts forming cracks and failing. So what they do, they put rods of steel inside of it, and they call it reinforced concrete. Now, this steel is the one carrying most of the tensile load, and the concrete is most of the compressive load. Of course, the steel can help against compression as well, but when it comes to tension, since concrete is no good at it, this steel here is going to help with that. Okay, so seeing more than one material in cross-section of objects, beams, and stuff is very common. And here, by no means my goal is to talk about composites here, okay? Composite is a course of its own, and talking about composites and material that are not isotropic, different E's, different directions, all of those things, fibers and so on, that is not what I want to get into. So right now, when I say composite, mostly I'm talking about two different material, and they could be embedded like this, or they could be separated like that. So how do we look at the strain and the stress distribution? The way that we do it, there are two ways. One way is we say, well, the thing we do is, first we have an assumption. Let's talk about the assumption. The assumption is these two material, when you put them together in the cross section, they are well bonded together very well. They are not separated from each other. So whether you glued them or whatever you did, you bolted them together, you welded, whatever you did, they keep contact and they don't separate at the boundary. They are bonded well together, and in other words, the strain will be continuous. Okay, so if this consider a point right above this boundary and a point below this boundary, and the amount of displacement for each one of them in the x direction, so 1 point here, 1 point here, if there is a discontinuity at this boundary, so this one goes a lot more than this one does, then these two layers, these two material will be separated off each other, and that is not we are assuming here. Okay. The other thing we assume is that both objects will be inside the linear region, and the strain relation is the Hooke's law. Okay, so these are the assumptions that we make here. Now, with these assumptions, since the displacement or strain is continuous at the boundary between these two here, that is where this boundary is, the strain is not going to all of a sudden have an abrupt change. It is going to be continuous. Okay, now how, we'll see, but if here we say that material 2 is the stronger material and material 1 is the weaker material, then of course, because the stronger material has a bigger E in it, correct, then you're going to have a smaller strain. So you see the strain is going to go like this, small, right? And then when it goes to the weaker region, you're going to have bigger strains. But when you transition from the weak to the strong here over this boundary, there is continuity. There is no abrupt change. So if you look at the profile of strain, it's a line, not like when you come to here, then you have a jump and then you go back and then you have the rest of it. Okay, but the stress is not like that. The stress follows what? E times epsilon. This is the Hooke's law. So although right above and below this boundary the strain is the same, but the E is different. So this is E1, this is E2, and in this case I assume E2 is bigger than E1. So because of that, the stress is not going to be continuous. So if you look at the stress profile, it goes like this. And then right here at the boundary, you're going to have a drop. So this drop here from sigma 2 to sigma 1, this drop here, that is because the E is changing. Okay, so the profile of a stress is not continuous, but the profile of a strain is continuous. Okay. And so what's the formula for the strain? Well, that's the same formula as before. Epsilon still equals negative y over rho, or negative k times y, where k is the curvature, rho is the radius of curvature. But sigma in region 1 is E1 times epsilon, and in the region 2, there is a typo here. In region 2, it's E2 times epsilon. Okay? Good. Now for neutral axis, first thing is, where's the neutral axis of this beam? For neutral axis, because remember that's the first thing, when we calculate this I, we have to know I is about the centroid, correct? So first thing is, where's the centroid? Now in the case of a beam that is not symmetric about the z-axis, neutral axis, and it's not rectangular, it's not going to stay on the middle. It is going to change. So where is it? For that, we're going to use the fact that here in this beam, we assume the net axial force on any cross-section is 0. So all of the sigma distributions that you have on section 1 and all of the one that you have on section 2, that summation should be equal to 0, correct? So if you have some sigma x1 here and some sigma x2 there, when you integrate each one of them over their own area, over area 1 and over area 2, these are the two axial forces. Some of them should be 0. Now for sigma 1 and sigma 2, we replace them with negative E1 ky and negative E2 ky. And since k is constant, you can bring it out, right? Or even at that cross section, at least k is constant. You can bring it out and simplify it, and this is going to be the equation that you use for the neutral axis. Remember, the neutral axis is the location of the centroid of the cross section. And the location of the centroid of a cross section is this one: integral of y dA equals 0 with respect to the if you take with respect to any location, this location, if you calculate integral of y dA and then divide it by a, that is going to be y bar. But if you put your axis at the centroid and you calculate this integral, this first moment should be equal to 0, correct? Now, in this case, if you look at it, that's not exactly that. But remember that area of section 1 and section 2 is equal to the entire area. But here, area 1 and 2, each one multiplied by E1 and E2. So this is how you get the neutral axis. Now, you might say, well, that kind of looks a little bit not as convenient as this one. You are right. And for that, I'll show you an alternative way to handle it. That is called the transform section method. Okay, and I'll show you that in the transform section method, the calculating the neutral axis is a little bit nicer. So you transform all of the beam into a single material of the weaker one and deal with it like you did in previous videos. Okay, so we'll get to this and we revisit this with a much more convenient way. And what about the moment curvature relation? So for moment curvature relation, the same formula as before exists, except now the total moment that you get is basically coming not only from a stress distribution on section 1, but also from a stress distribution on section 2. So you have to add them together, where sigma dA was that force and y was the distance from the neutral axis. So that is a moment. This is a moment term, this is a moment term, add them together, replace sigma 1 and sigma 2 from these two that you had above here, and with those specifying and simplifying, this is the equation that you would get. Now, the kappa, the curvature, you can factor it out, and then this is I1, this is I of section 1 here, this blue section, and the other one is I of section 2. So K times E1 I1 plus E2 I2, that is equal to the total moment. Therefore, kappa, or half of the, the reciprocal of the radius of curvature is going to be M over E1 I1 plus E2 I2. For a single material beam, if you remember, kappa was M over EI. But now your EI has two components, so you have to multiply and add them together, as you can see. Similarly, sigma, that was negative M over EI, MY over I, this one. Now, if you look at it, there are two sigmas. In each section, there is a different sigma. First of all, or if you want, you can write it like this: negative MYE over IE, correct? You can write it like this. Now, instead of this IE, this modulus, this bending stiffness or rigidity, you have to replace it by E1 I1 plus E2 I2 for both of them. Y is still Y, M is the same M, but E for section 1 is E1, for section 2 it's E2. So you see that the stress has some discontinuity in it at the boundary of the two objects, because the strain is the same all over the place, but all of a sudden you jump from stress with proportion to E1 with the stress proportion to E2 here. So this is how to calculate the stress, this is how to calculate radius of curvature, and this is how to calculate the neutral axis. But as I said, the better way to do it is to convert the entire beam into one single material. We call it the method of transform section, and then I'll show you that it is much easier to solve problems with that method. So what we do in the transfer section method, we define a ratio called the modular ratio, which is the ratio of the bigger Young modulus to the smaller one, or the E of the stronger section to E of the weaker section. Clearly it's bigger than 1. And then we're going to convert all of the cross-section into a cross-section of a single material, in this case the weaker material, And the way we do it is we increase the width of the stronger section to n times whatever it was. So if this is the cross section that I have, right, the bottom portion is material 2, the stronger one, 1 is the weaker one, and b is the width of the material, and h is the total height. So I keep material 1 as it is, but section 2, I make it n times bigger, so I make it a width of n times b. And now I assume this whole thing is made out of material 1 as opposed to 1 and 2. It's a uniform material, it's a homogeneous thing. And now I find the neutral axis for this cross section, this T as opposed to that rectangle. I find that, and then I find the stress and the strain accordingly, right? So first thing is, where is the cross section for this? Well, remember, to find the cross section, this was the equation that we had, E1 integral of y d1 over 1, E2 integral of y dA over 2 is 0. I use that, but now instead of E2, I replace it with NE1, and I get this, and I get rid of E1 from both sides, and I get this equation. And if you look at this, just looking at this, you see that the first moment of the weak section is added to the first moment of the stronger section, which is multiplied by n. Now, how can you make the moment of the stronger section n times bigger? As I said, the solution is to make it n times wider. Because remember, it's parallel to the z-axis, so this dimension, whatever it is, it has power 1. Remember, I for this section is bh cubed over 12. As you see, is proportional to b to the power 1. So if I make it n times wider, I'm making I n times bigger, or a n times bigger, and for that, I can basically consider this to be the finding this basically the original one that we had for a uniform material. I can use this one, but for that cross section, if I use the simple centroid equation that I had for a simple cross section, but on this modified or a transform cross section, these two are going to be the same result. Okay, so I transform it, and now I'm going to only apply whatever I knew for centroid. I'm going to apply to the transform cross section. That will give me the location of centroid, which is also the neutral axis here. And let's say it's right here, for instance. Good. Now that I have that, how do I go about finding the stresses? Well, remember, sigma is an strains. Remember, strain epsilon was negative y over rho, correct? Or if you want to do it based on the moment, we can also do that. This is sigma over E, and sigma is negative my over I, so it's going to be negative my over EI. So clearly, as you remember, we said that epsilon is going to, or strain is going to stay continuous. So now this is basically the profile of the strain. You see, there will be no discontinuity. It is going to be uniform, and it has no changes at this boundary here. But the stress is not like that. The stress is going to start from 0 at the neutral axis, and it's going to go up. On the other hand, this is on the weaker material, directly go up. But on the stronger material, look, you only continue this linear relation until you get to the boundary, from the centroid to the boundary, or neutral axis to the boundary. It goes with a similar slope. Once you get there, now your slope changes to n times whatever it was. And so again, this sudden change in the stress at the boundary location is because of changing in E. So this is going to be your stress diagram. This is going to be your strain diagram. And if you want formulas for that, sigma in the weaker material still negative my over I. Which I? The I is the I of this combined section. So the I of this combined section, I call it I total, and that is I of section 1 plus n times I of section 2. Which I? This I. So when I say I, 2, I'm talking about this I. If I go with this transform version, then this is already n times I2. So basically IT is the moment for this transform version. If I calculate I of this transform version, it is already IT, which I can use in my formula. So you see sigma 1 is the same formula that we had for a uniform material. That's the exact same thing, negative my over I, but I is for this transform section. Now for material 2, that's the exact same thing, except it's n times bigger. So it's negative n my over I t, and that's all it is. Okay, so this is the equivalent or total moment of the transform section. This is sigma in material weaker and material stronger based on this ITM and Y, and the N, the modular ratio. And this is how to find the neutral axis in the transform section, which is basically based on what we learned from statics. Now, to put this all in practice, here we are going to look at this example that you have two plates or faces of aluminum on the top and bottom, material 1, which has 72 gigapascal Young modulus, and in between you are going to fill it with a plastic core, and the plastic core has a Young modulus of 800 megapascal. The thickness of the plastic core, the height of the plastic core and the height of the aluminum plates are given. The width of the cross section is given, and the basically the moment that the beam is undergoing, it's a uniform bending moment, and it's 3 kilonewton meters. So here we assume it's uniform bending. And what we need to find is the maximum tensile and compressive stress in the whole cross section. And again, this is a simple case because M is constant. If it's not, then you have to go and look at the shear and the bending moment diagrams, and in the bending moment you find maximum M. Okay, so what do we do here? N is going to be the bigger E to the smaller e. Now we don't need to follow this formula, right? So it's not always 2 that is stronger than 1. Whichever that is bigger, you divide it by the smaller one. Okay, so in this case, material 1 is stronger than material 2. So N is E1 over E2. Okay, pay attention to that. This N is always bigger than 1. And this is 72 times 10 to the 9 giga, and that is 800 mega. And if you simplify, this is going to be like 90. Right? Because this is like 0.8 gig, this is 72. So the ratio is 90. That's a huge ratio. And if that's the case, then this cross section you can transform into something like this. That this middle section stays like this, but this top section and the bottom section are going to be 90 times wider. And here, I don't really want to go 90 times wider because I cannot fit it into the screen. But basically, the width of this guy is going to be 200 mil. But the width of these guys are going to be 90 times 200 mil, which is basically 18,000 mil. Now you can assume it's all made of material 2 all over the place now. But with this huge I cross section as opposed to a rectangular one. And now, first of all, in this case, you're lucky the centroid's still gonna stay at the center. Okay? The centroid is still gonna stay at the center because it's symmetric. If it wasn't, then you have to find it for this I cross section. And you know how to do that. It's not really a topic for this video. But the only thing is the IT, this big guy, has to change. So I for the section 1 is whatever it was, so it is still B, which is 200, and I write it in meters unit, 0.2, times the height of it, which is 150, cubed over 12, and then plus 2 times, because you have 1 on the top, 1 on the bottom. Now for these guys, what is the I for these ones? First of all, their thickness is still 5, but their width is 1800, so it is going to be 1800. Now you have to get rid of 3 zeros, so it's going to be 18 times 0.005, which is 5 mil, cubed over 12. This is those with respect to their own centroid, but their centroid is away from the centroid of the whole beam, so you have to use parallel axis theorem. So you multiply their area, which is 18 times 0.05, that's their area, times some distance squared. Which distance? The distance between these centroids. How much is it? Well, this is 150, so half of it is 75, and this is 5, so half of it is 2.5. Correct? So the whole thing is going to be 2.5 plus 75, or the whole thing is 77.5. Correct? That is the distance from the centroid of each one of these with respect to the neutral axis of the beam. So it is going to be 0.0, correct? 77.5 mil squared. It is going to be like that. This is going to be I of the total. And so we can find the number for this case. So let's find this. So you are going to get 0.0011 meter to the 4. This is the I total for the transform cross section. Now that you have that, we can go ahead and calculate the stress in each section. So for section 1, which is the weak section, the formula is still the same. Sigma, you can find it, correct? So sigma max and min in this case is plus and minus y max times m over I total. Now y max and y min for this section is half of 150, which is 75. That's 75. M is 3 kilonewton or 3000 Newton. And I is this number. So whatever you get is going to be in Pascal. So it is going to be plus and minus. So it is going to be 0.205 megapascal. Okay, so this is plus and minus. This is maximum and minimum, or maximum tensile and maximum compressive stress within the plastic. This is for section 2. Now for section 1 is simply, what you need to do is you have to find their y's and then multiply it by n. So if I want the sigma max and min in section 1 in the aluminum as opposed to plastic, again, this is plus and minus, and the way I write it, because it's symmetric, y max of this section times m of that over it, and then the whole thing times n. So in this case, your y max is, if you look at it, it is 0.08. It's 80 mil. So it is 0.08, not 0.075. M is still the 3000. N is 90. And IT still this number. So if you do that, you're going to get plus and minus 19.636 megapascal. Okay, so these are the maximum and the maximum tensile and the maximum compressive stress for the plastic core and the aluminum faces based on the method of transform cross section that I just explained. Or we could go with these top formulas, and if you went with those, you would get the exact same number. But I always prefer the transform section method because it's much easier to understand, and you can use the formulas that you learned already in previous videos. So hopefully the video was useful to you. I'll see you in the next lecture.